integrated sensing and communication webinar series. I am Jie Xu from the Chinese University of Hong Kong, Shenzhen. Today, it is our great pleasure and honor to invite Professor Yonnia Eldar to give us a talk. Professor Yonnia Eldar is a world-renowned researcher in signal processing, machine learning, communication, and radar, etc. Today, she will give us a talk about the deep analog to digital compression and its application to automotive radar and massive MIMO. So first, let me introduce our distinguished speaker. Professor Yonnia Eldar is a professor in the Department of Mathematics and Computer Science, Weizmann Institute of Science, Israel. She was previously a professor in the Department of Electrical Engineering at the Technion, where she holds the Edward Chair in Engineering. She's also a visiting professor at MIT, a visiting scientist at the Broad Institute, and an adjunct professor at Duke University, and was a visiting professor at Stanford. She received the BS degree in electrical engineering from Tel Aviv University, Israel, and the PhD degree from MIT. She's a member of the Israel Academy of Science and Humanities, an IEEE Fellow, and EUROSAFE Fellow. She has received many awards for excellence in research and teaching, including the IEEE Signal Processing Society Technical Achievement Award, the IEEE AESS Fred Nelson Memorial Radar Award, the IEEE Keiyo Tomiyasu Award. Also, she received numerous other awards, as you can see from her bio. She received several Best Paper Awards and Best Demo Awards together with her research students and colleagues. She was elected as one of the 50 most influential women in Israel and was a member of the Israel Committee for Higher Education. She is the editor-in-chief of Foundations and Trends in Signal Processing and a member of several IEEE technical committees and award committees. Okay, so before we start, I would like to mention again our Q&A rules. So during the seminar, all the audiences will be muted. So please type your questions and send them to me through the chat box. And I will connect all the questions from audiences from Room and also some other audiences from offsite live broadcasting. And during the Q&A, we will choose 3 to 5 questions to ask the speaker. And the questions will be named. So we will encourage the questions to unmute yourself and ask questions by yourself during the Q&A session. Okay, without further ado, let's welcome Professor Yonnia Eldar. Professor Eldar, the screen is yours.
Thank you very, very much. Let me just share this screen. Okay, great. So can everyone see my screen?
Yeah, it's quite clear.
Okay, perfect. Perfect. So first of all, thank you so much for that very, very kind introduction and, for inviting me to give this talk. I think one of the maybe positive benefits of COVID are talks like this. And I think it's a wonderful thing for the community to be able to connect and hear what different people are working on. So hopefully this will stay with us, way beyond COVID. I also want to wish everyone who's connected here today. I know, different parts of the world have a different situation now in terms of COVID. So hopefully we will hear good news from all parts of the world. And I want to wish everyone and their families a lot of health. So with that, let me begin. So what I want to talk about today is something that we, and of course, many other groups have been working on, where our goal is to try and acquire and process signals using as least resources as we possibly can. And we're going to do this by combining ideas of signal processing and also ideas of machine learning. And what we'll try to show is that this could lead to interesting new ways of sensing information that could potentially lead to new technologies, which could have impact on things that are maybe closer to the topic of the seminar, radar and communication systems, but also in applications beyond engineering, such as different applications in science and medicine. And we'll give some examples to that as well. So today, data is being generated at exponentially growing rates, and that creates a lot of bottlenecks. So we're spending a lot of power on acquiring this information. We have to worry about storage. So there's about 3 million data centers like this data center that you see over here worldwide, just to store all of these bits that we're generating. Processing becomes very complicated. Communicating these bits, of course, is very demanding. And, a recent prediction by Cisco predicted that the internet traffic will approach zettabyte. So that's 10 to the power 21. That's, really a huge number. And the question we want to deal with today is whether we really need all of this data. So we're generating, essentially all of the data that we possibly can. And we always think that data is good, but the question is whether the price we're paying for that may be too high. And do we actually need this data for the tasks that we're interested in? So that's really what we want to talk about today. Well, why would we think that we don't need all of this data? There's many examples where we could show that we're actually not using all of the data that we acquire. So for example, if we look at medical imaging, which is something that we've been working on a lot, we're acquiring much more data than's actually being projected at the end on the image, which is the doctors are using to make a clinical diagnosis. So for example, in ultrasound, it's very similar to radar. We're acquiring many channels of RF signals, but all of this data is projected at the end onto a very simple image of this form. So clearly not all of the data is being used for making a diagnostic decision. If we think of smart cities or autonomous vehicles, again, applications that have been very hot recently, we're putting all of the sensors that we can, so LiDAR, radar, vision, but at the end, when we need to make specific decisions, we're not using all of this information. And maybe the most prevalent example is that of deep neural networks. So we know, of course, today we could train networks using a lot of data to perform a variety of different tasks. So for example, for classification, but we know that children could classify, for example, dogs and cats by seeing, maybe only 1 or 2 examples. So clearly we're not being efficient about the way we're processing the data. And the question is whether there's a better way to acquire only what we actually need. Hello, girl, in a digital world. So this is a cool song by Judy Gorman, which resonates very well for this topic of acquiring information. And today, of course, all of the processing is being done digitally, which means that we first have to acquire this analog information and convert it to a digital format for processing. And as we all know, the way we do that today is first by sampling in time and then quantizing the samples in time. And this is guided by the well-known Shannon-Nyquist theorem. So the sampling rate has to be at least twice the highest frequency, and we have rate distortion theory that tells us at what rate we need to quantize the data. So this is the paradigm behind all the digital applications. And in fact, if we actually look at the way acquisition systems are built today, they're built in a very modular fashion. So suppose, for example, we want to acquire a radar signal. What we would do today is that we'd first sample the signal at a rate proportional to the signal's bandwidth. Okay, so we have the samples in time. We would then go ahead and quantize them. And typically the rule of thumb in quantization is that for every bit that we add, we get 60 B in SNR. So depending on the SNR that we want, we're going to add more and more bits. And only after we've done these 2 procedures of sampling and quantizing, so basically this is the acquisition process, only then do we start thinking of the task we want to perform. So for example, in radar, we might want to perform beamforming to look at a specific direction. So this is already a digital task, and the output will be, let's say, our delay Doppler map. So we're sampling and quantizing at rates that ensure that we could recover this underlying physical signal. But at the end, we're actually not even interested in the signal. We're interested in this delay Doppler map. So we're doing things in a very modular fashion where each block is optimized separately, and it's not taking the actual task we care about into account. So this still works, right? This is the way systems work today. And the question is, so, if it works, why fix what's not broken? Well, the problem is that it works, but it works at a cost. So today, if we want to get, large bandwidths for high resolution or high rate communications, we have to use samplers and quantizers that are operating at very high rate. This consumes a lot of power. It's very costly in terms of hardware. Sometimes it's just too high of a rate. We can't accommodate it. And if we look at different trade-offs, like for example, in medical imaging, the high rates will translate into long scanning times or high radiation dosage. It might mean, long time on target. So it's not just the cost of the hardware, but there's other trade-offs, physical trade-offs as well. So at the end of the day, this ADC that we kind of take for granted actually leads to a variety of different bottlenecks. And the question is how we could overcome it. So what we're going to suggest in this talk today is what we call task-based structured acquisition, where the main idea is, first of all, to do joint design. So no longer to look at these blocks separately, but we want to design them jointly. And in designing them jointly, we're going to take two things that are very important into account. So the first is this structure, where it could be structure in the input or structure in the system itself. And the other is the actual task we're interested in. So intuitively, if I want a delay Doppler map, I should need less samples and less bits than if I want to actually recover the underlying signal. Now, what we'll also show throughout the talk, and we'll focus on it at the end, is that these same ideas of structure and taking into account the task can also lead to what we call model-based deep learning methods. So we could get data-driven methods that are also much more efficient and also interpretable. So this joint design could lead to a variety of different advantages. We'll see that we could get very compact portable devices. We could get joint radar on communication systems, since each one of them is done efficiently. We could get efficient wideband sensing. We could get cheap and high resolution radar, efficient MIMO systems. We could develop a new methodology for getting low bit quantization without paying a price. We could see that this could also lead to super resolution, and we'll see some examples in microscopy and ultrasound. And finally, like I said, this can also lead to advantages of model-based deep learning. So that's kind of the overall philosophy that we want to put forth today. And this is a more detailed outline of the talk. So we'll start by talking about structure and see some applications to ultrasound and radar. We'll then talk more about the tasks, how we could exploit tasks, and see application to radio, to microscopy, and to different problems of quantization in massive MIMO systems, in multi-antenna systems, and in joint radar communication systems. And finally, we'll end by showing how we could also use these ideas for model-based learning. So let me say, I know there's a Q&A at the end, but I'm also happy, if it works with the organizers, to take questions as we go through the talk. So if there's questions, I'm happy to answer them as I'm going through as well. All right, so let's start by talking about older work, which was how we could exploit structure. And then we'll move on to see how we could exploit the task and see some newer applications to communication and radar. So what you see here on the slide are different systems that we've developed in the lab that are based on the principles I'm now going to show. And I'm saying this because it's important for us to show that these ideas are not just theoretical, but they can actually lead to new system designs. So one of the first examples we looked at for structure is this multi-band problem, where I have a signal that consists of several bands of information. Each one of them is narrow, but they could be spread over a very wide regime. Now, of course, signals like this, I could still operate at the Nyquist rate, but when I sample at the Nyquist rate, I'm actually accommodating arbitrary signals with arbitrary bands, which does not fit our model, because we know that our signal will never occupy the entire bandwidth. So clearly this is wasteful, but the question is, how do I sample these types of signals when I don't know the carrier frequencies? Now, although we're giving this example in the context of multiband signaling, the same example appears in different forms of imaging whenever we're using multiple frequencies, like multispectral CT and multispectral imaging. So this is one example of structure in the frequency domain. Another example, actually, in the time domain follows from this very nice framework of finite rate of innovation, first initiated by Martin Vetterli and his group. And a very popular example of this is radar, where we send a pulse, and what we're getting are reflections of this pulse from the different targets. And what we want is to determine the time of arrival, which will tell us the distance to the target, and the velocity, where if we get consecutive amplitudes, we could determine the velocity. Now, the same model appears also in ultrasound, where we send a pulse through the ultrasonic probe and we're viewing reflections from the tissue. And if we can plot the times of arrival and the amplitudes, then we get one line in the image. So in these cases, if we could exploit the pulse structure, we can also use fewer samples and also get higher resolution. Now, the ultrasound example is actually more tricky than radar, and that's because the ultrasound example is actually a near field example, and it's also a very noisy example. So the ultrasound environment is very noisy, and therefore, within this probe, we typically have between 128 and 256 elements. And in order to improve SNR and focus the beam, because it's near field, we actually perform beamforming, but it's a nonlinear beamforming. So we have to align the signals on these nonlinear time grids, where the nonlinearity just comes from Pythagoras' theorem. So computing the time of arrival of each one of these signals. And then we can focus the beam to a point in the image. So we have to repeat this for every point in the image, and this is very costly. So here the problem is not just to sample at lower rates, but if we sample at a lower rate, the question is, how do we do this alignment on this fine grid if we don't have samples on a fine grid? So this brings us to this task-based idea, where not only do we want to sample at a low rate, but we want to be able to do all of the tasks, all of the processing at the low rate as well. And here, for example, and we'll see how we do this later on throughout the talk, we develop what we call compressed beamforming. So not only do we sample at a low rate, but we do all of the processing at a low rate. And this gives us several advantages. So it allows us to reduce the machine, actually get rid of the machine, and just have a simple probe and some platform for imaging. It allows us to increase the frame rate to enable 3D imaging. So we'll see applications as we go through the talk, but this is a nice example of both structure in the signal, but also a specific task that we're actually interested in. So I've shown two examples. There's many more examples. I don't want to elaborate too much on this part because this is kind of older work, but let me just say that we can show that all of these examples and many other examples of structure fit under this model of a union of subspaces. So we can show mathematically that they all fit this union of subspaces model, where basically we're saying a priori we have a large set of possible subspaces, and we know that our signal lies in one of them. We just don't know a priori which one. And what we can prove is that just by the fact that we know that the signal is in some low dimensional subspace, even though we don't know which, we already get a low rate sampling theorem. So the theorem tells us that the rate at which we need to sample the signal is the rate associated with the sum of two subspaces in the union, irrespective of the number of options. So the Nyquist rate would be the sum of all options, which will be very high. And this theorem says we only need the sum of two. So that kind of paves the way to sub-Nyquist sampling, but of course it doesn't tell us how to do it. It just says that that's a minimal sampling rate. Over the years, we've developed what we call the sampling paradigm, which allows us to actually achieve this in practice in many different applications. And all of these different boards that you see over here for different applications follow the same paradigm. So the idea is that we take our signal, we alias it, so we mix it. And in a sense, what we're doing abstractly is we're taking all of those possible subspaces and we're projecting all of them onto some low dimensional subspace. Okay, so let's say in this multiband example, we're multiplying with a periodic function in time, which means in frequency, we're convolving with the delta train. And after convolving this with the delta train, we're basically getting this picture shifted all the way to the right, shifted all the way to the left, and summed up. So we get this aliasing, this mixture of all of the components. We filter it so that we look only in the low pass regime, and then we could sample it at a low rate. So this is the analog side. We're basically doing analog pre-processing and then sampling using simple off-the-shelf components at a very low rate. And then after we've done all that, to recover the signal, we're using compressed sensing ideas, not for sampling, just for recovery, where the compressed sensing will allow us to locate the correct subspace, and then we could do analog recovery within that subspace. So this is the basic paradigm we've used in all of the applications to exploit structure. We can show a variety of different optimality properties, so we can show that it minimizes the mean squared error in the presence of noise. It's optimal from a capacity point of view if we're thinking of a communication channel, so it has various different forms of optimality. And we can also build it in practice, which is what is important. So the way compressed sensing here comes into play is, again, not in the sampling because these are analog signals and not vectors, but we use compressed sensing to locate the correct subspace. So I'm assuming everyone is familiar with compressed sensing, and it's not so important for the rest of the talk, but just to complete the picture for those who maybe are less familiar with compressed sensing, just a very compressed slide on compressed sensing is that compressed sensing allows us to recover sparse vectors, vectors that have a small number of non-zero values from a small number of measurements, where the measurement metrics has to sufficiently mix the input vector. And the point is that we could do this very efficiently. So for those who want more background in it, you could see our book on compressed sensing for many more details. So that's kind of the vanilla compressed sensing. Over the years, there's of course been many, many extensions by many groups of that basic linear model. So in our group, for example, we've worked a lot on extending the sparse recovery or compressed sensing to the nonlinear domain. And this is particularly important in optics. So we've worked a lot on phase retrieval using compressed sensing and more general nonlinear compressed sensing. We've worked a lot at reference-based compressed sensing. So what do you do if you have a series of images, not just one? And this is very important in medical imaging, for example, in MRI. We've looked at combining compressed sensing with tracking, for example, in ultrasound, where I'm trying to look at blood flow. So I have more information by tracking the blood itself. There's been a lot of work on statistical sparsity, and in recent years, there's been a lot of work by many groups, including our own, on replacing the standard compressed sensing algorithms with deep learning methods that could both work more efficiently and also relax the strict sparsity conditions. So this is kind of just a very, very brief summary of a lot of the exciting work that's being done in this area, and all of that we could connect to the general sampling paradigm to allow for more extended types of functions. So just putting it all together, we have the analog part, we have the digital recovery by using these extended compressed sensing ideas, and that allows us to build devices that when their structure could sample at very low rates. And these are very simple practical devices. And here you see some of the devices that we've developed over the years in our lab. And those who want more detail on the theory and the implementation could check out our book on sampling theory, where we go into much more detail on how to exploit structure and how to actually build these devices. Okay, so that kind of sums up the theory of how we do this. And I want to move on to show some applications where the applications will also go into some extended ideas beyond the basic vanilla ideas we've shown right now. So one of the paradigms that are very important to us in our lab is, this famous quote by Einstein: in theory and practice are the same. In practice, they are not. And what hopefully I'll convince you is that you could get things to work in practice as well, but you have to kind of work, we develop the theory, we go into the lab and try to build things, often it doesn't work, but then instead of trying to tweak it, we try to understand fundamentally, what was wrong about our model, fix the model, and then, get it to work. So hopefully I'll convince you that these things work in practice as well. So let me start with an application to ultrasound, because to me, this is one of the exciting applications, and everything we're showing for ultrasound is kind of one-to-one with radar as well. So in ultrasound, we've shown that we can actually create ultrasound images using these ideas at 4% of the Nyquist rate at every channel, and we can also dilute tremendously the number of channels. So overall, we could get an over 2 orders of magnitude savings in the data rate. And this leads to several exciting clinical applications. So it paves the way to 3D imaging, which today is limited by the data rate. It allows us to do things quickly, which is very important, for example, in cardiac imaging. And maybe the most exciting application, at least to me, is that we can actually get rid of the machine. So instead of having this big machine that we have today, we can do everything within the probe. Since now we're sampling at a low rate, we could just sample at a low rate within the probe. Today, sampling is done in the machine, not in the probe. The probe is entirely analog. It transmits and receives, but it doesn't digitize because of the high rates. That's why you have this big cable that basically the data goes through analog into the machine, and only in the machine is it sampled and quantized. So now, because we can do it at a low rate, we can actually do it within the probe. And then what comes out of the probe are the actual bits that represent the response of the tissue. So it's not an image, it's just the actual bits. Those bits could be transferred over any standard Wi-Fi channel. We could then recover an image just like is done today, but we got rid of the machine. Or we can actually look at those bits and ask ourselves, is there something better we could do than just recovering the image the way it's done today? So let me show you a quick demo.
I would like to show you here a demonstration of a normal heart. What we can see here is an echocardiography.
So this is one of the doctors we're working with, a cardiologist, Dr. Shai Taiman, and he's scanning one of my former students that I get. This is just used for powering purpose. The data is going from the probe to the local machine, to a remote machine via the cloud, and to a tablet.
We can see the mitral valve and the tricuspid valve. We can see the nice motion of the leaflet.
Again, this is cardiac imaging, so it's real time and very fast.
Function, and there is no pericardial effusion. The picture itself is very good, very crisp, and we can demonstrate very nicely this subject's heart.
Okay, now he's scanning directly to a tablet. So we could totally get rid of the machine. The other really nice thing is that now we have this channel data available to us. So we have the actual bits that are coming out of the tissue reflection and not just an image. And we started a new clinical forum with doctors both from Israel and abroad that we're working with to try to work on, now that we have this new source of information, what could we learn from it clinically beyond just an image? So to me, this was an exciting example of how, by a new acquisition strategy, we're actually getting to totally new clinical applications just because we have new types of data that are available to us. Now, like I said, everything we did in ultrasound, we could do also in radar. Of course, the benefits in radar are different than the benefits in ultrasound. So I'll talk briefly about that. I'm not going to go into too much detail here, but those of you interested could see our recent book on compressed sensing in radar, where we go into much more detail. So this is just a quick movie of some of the things that we did in radar, and we'll talk a little bit more about them later on in the talk as well. So in radar, the basic trade-offs that we have are, of course, between range and, range, resolution, and bandwidth. So if we want better resolution, presumably we need larger bandwidth. If we want better Doppler resolution, then we need longer dwell time. And of course, if we want better angular resolution, then we need more antenna elements. And using the ideas I've just presented, we could actually break all of these trade-offs. So again, just like we did in ultrasound, we developed this sub-Nyquist paradigm, which allows us to break these different trade-offs. So this is the actual board. What we're doing in practice is that instead of sampling the entire bandwidth, we're sampling only several bands. And of course, that allows us to lower the rate, but it preserves all the information. So here you see real data with a lot of noise, a lot of clutter, and you'll see that we still get a very high range resolution delay Doppler map, even though there's a lot of clutter and noise. Now, the other nice thing is that because we only use several bands, we can now work in a cognitive fashion where we coexist with communication channels. So we could locate, where the communication signal is, and then send information only in those vacancies. So we'll get the same resolution as if we sent over the entire bandwidth, but we're only sending in part of the bandwidth. Now we could do the same thing in terms of time of target. So instead of sending all the pulses in one direction, we could send the pulses in multiple directions, and in each one of them get a high resolution delay Doppler map. So this is what you're seeing over here. You're going to see two directions. We could do this for more as well. And both of them, we're getting very high resolution delay Doppler maps, even though the overall time is the same as what you would do today in a single direction. And of course, you could transform all of these ideas spatially so that you dilute a MIMO array and still get very high resolution. In fact, we use fewer elements and get higher resolution than what you would get in a standard MIMO system. And that's just because our recovery algorithms are more powerful. So more recently, we've been taking these ideas to the automotive radar regime. And there it's both the idea of coexisting with communication channels is very important, and also the idea that we could look in multiple directions at the same time. So we've recently showed a demo in ICASP, which shows how we could do this in the automotive domain. One of the issues that comes up when we're looking at automotive radar is that until now, the ideas we showed presume that we know the pulse shape. So we don't know, of course, the time of arrival, but we know the shape itself. That's not always true when we look at very complicated environments. And what we were able to show is that we could do this in a blind fashion as well. So even if we don't know the pulse shape, we could extend the theory to do both blind deconvolution and this super resolution and target localization from sub-Nyquist samples. So this is a recent demo that we showed where we do this in a blind fashion. And the price we pay is that we have two receivers. So instead of having one receive chain at a sub-Nyquist rate, we have two receive chains at a sub-Nyquist rate, but still the overall sampling rate is much, much lower than the Nyquist rate. And both of these receive chains are very simple. They're both sampling at a very low rate. So that's what this demo shows over here. And all of the movies that you see in the talk are available on my webpage. So I know I'm going through this quite quickly, but you could see them in more detail on our webpage. So this shows an automotive application where even though we don't know the pulse shape, we could sample at a very low rate, much lower than Nyquist, and still get a perfect delay Doppler map, even without knowing the pulse shape. We've done the same thing spatially, like I said, so we can take an antenna array like this antenna that you see over here and only use a small number of the array elements. We've developed a deep learning method to choose, a model-based deep learning method based on these models to choose which elements to use. And what we can show is that we get very good direction of arrival recovery, even though we're only using a subset of the elements. So here you see real measurements that we did at the Weizmann Institute, where we used this sub-Nyquist array. This is in the lab. Outdoors, we use the smaller version of it, but it's doing the same thing. And we use these sub-Nyquist sampling ideas, both spatially and in time, to show that we could get very good direction of arrival, even though we're using both a sparse array and each of the antenna elements is sampled at a very low rate. So that's what this demo is showing. And again, we're doing this all in the context of automotive radar. Okay, so hopefully that gives you a little bit of a sense of what we could do in the regime of exploiting structure. And I want to change gears now and look at how we could take different tasks into account. So we've already seen some tasks, right? Like delay Doppler is a task and beamforming is a task. But the question is if we could do this more generally. So, if I want not to recover the signal itself, but I want to recover a function of the signal, could I actually exploit that in order to reduce the sampling rates? And what we've shown in many applications, I'm not going to go through all of them today, is that since we only need a function of the data and not the data itself, we can actually sample and quantize at much lower rates. And what we'll do now is see some examples of this. And on the slide, there's more examples. We'll go through several of them in a little bit more detail. So the first application I want to look at is power spectrum reconstruction. This is an application that appears very frequently, for example, in array processing, in imaging. We'll see some examples as well, where basically I'm sampling a signal, but I'm not interested in recovering the signal. I'm interested in recovering the second order statistics of the signal. And the question is, if I only want the second order statistics, could I somehow sample at a much lower rate? So, this is a very interesting sampling question, right? Put applications aside for a minute. At what rate do I need to sample a stationary signal to recover its covariance? And surprisingly, there's not a lot of work in this in the literature. So there's been in the past few years, there's been some interesting results in our community, but they don't treat the most general problem, which is what we want to do over here. So before I go in to show the solution, I guess the question is, why would we expect that we could reduce the sampling rate, right? I'm not assuming any structure. So I want to give a very simple illustration, which hopefully will help answer that question. So suppose, there's some function that we're interested in sampling, and we have our sampling set you see over here. And this sampling set is very sparse, so it's not going to satisfy the Nyquist rate. So, it's not going to be enough to recover the signal because we're not assuming any structure on the signal. But now if I only want to recover the power spectrum, then in fact, I'm not interested in the sampling points. I'm only interested in the sampling differences, because we know that the power spectrum or the covariance function depends only on the differences between sampling points. So if I have n points over here in the difference pattern, if I choose the points correctly, I can have n squared points. Okay, and therefore I can imagine that even though I can't recover the signal, I can recover its power spectrum because I have n squared points. Okay, and we could actually, that was just kind of intuition, but we can make that more substantial. I won't go through the math here, but we can prove mathematically that we could come up with sets that the density of the set itself goes to 0, so it's not sufficient to recover the signal, but the density of the difference set will go to infinity, and therefore it's sufficient to recover the covariance. So I'm going to skip the mathematical details. The nice thing is that we can prove general theorems, and we can also give many special cases that will satisfy that theorem, which means that we could sample at very low rates and still recover the covariance function. So what I want to do next is show an example of that, specifically for cognitive radio or power spectrum recovery. So in cognitive radio, we basically want to know where there's holes in the spectrum so that we can allow secondary users on the channel. So what I want to show next is a short demo that we've developed in the lab for cognitive radio. Why is this not playing? I'm sorry, one sec. Okay, good. A short demo for cognitive radio, and this is a review that we wrote on the topics that you could go ahead and see some more details. But here we see an example where the input signal has 3 gigahertz spectrum, so the Nyquist rate is 6 gigahertz, and we're sampling at only 6% of the Nyquist rate, and we could still perfectly recover the spectrum of the signal. So what you're going to see here at the top is the signal varying in frequency. Here you see the sub-Nyquist sampling, which of course just looks like garbage, but after our recovery methods, we could get very good recovery of the signal and its spectrum, and this is very robust to noise. It doesn't depend on any specific properties of the input signal, so it works in a variety of different areas, and if you look at our review, you could see much more details on the method and how it works in practice. So now I want to show a totally different application that's not related to communication and radar, to super resolution. And we'll see that we can use this idea even in problems that are basically not sampling problems. So super resolution microscopy is a really interesting field. We've been working on it quite a bit. We know that, optical microscopes are very simple and very powerful, but they suffer from the diffraction limit, which means that we cannot see details that are smaller than half the wavelength used for illumination, which means in practice that when we look at the optical regime, we can see bacteria and cells, but we won't be able to see proteins and small molecules. Now, in 2014, the Nobel Prize in Chemistry went to this really clever idea of super resolution microscopy, where the idea was to use fluorescent molecules and control them. So instead of taking one image, we now take thousands of exposures or thousands of images, where in each exposure, we control the fluorescence so that only a small number of fluorophores are actually fluorescing. And then you just think about it as like you're looking at a series of images. In each one of them, there's only, let's say, 3 bright spots, and then you could just stick a Gaussian every time you see a bright spot and sum over all the images. So this allows you to get super resolution and led to the Nobel Prize. So you could get down to 20 nanometer spatial resolution, but this is done at the expense of temporal resolution, because now to get a single image, you're actually taking thousands of exposures, which means that you can't do live cell imaging using this. So what we wanted to look at is whether we could get the best of both worlds. We want to get good spatial resolution, but we also want to get good time resolution. And here we use this very powerful idea of power spectrum recovery. So these images are basically brightness images, which means that it's enough to recover in each pixel the variance. And therefore, we've just shown that we could recover variance from a small number of exposures. And this leads to our method, which we call SPARCOM, super resolution correlation microscopy, because we're basing it on the correlation. And what you see here are some examples. This is simulated data, this is real data. And you see that our method, SPARCOM, could use much fewer frames than the method behind the Nobel Prize Storm. We use 2 orders of magnitude less frames, but we get even better spatial resolution. So here you can see a cavity that you can't even see in the Storm image using much less data. Now we can actually take this even one step further using the model-based learning ideas I'm going to show later on. So we keep the structure, but just do this in a learned fashion. And in this way, we don't even have to know anything about the microscope. So here we assume that we know the point spread function of the microscope to get these results. And in the learned version, we actually get better resolution, training from a single image, very good time resolution, and we don't have to know anything about the system. So this is not a sampling problem, right? Everything here is discrete to begin with, but we could use the sampling ideas to get super resolution. So now we've been doing some exciting work with the group of Professor Gilad Daran at Weizmann to actually use this for live cell imaging. And in particular, he's interested in T cells. And we got really first results that show that we can now do live cell imaging using these ideas. Another interesting application of these ideas is actually to ultrasound. So, ultrasound suffers from resolution limits, but of course we can't inject fluorophores into the body, or we don't want to inject fluorophores into our body. But what we could do instead is use these contrast agents. So this is, Sonoview contrast agents, particular type of microbubbles that people use for contrast. So it's FDA approved, it's used to improve contrast. And what we thought of is to say, anyways, people are injecting this into bloodstream for contrast, but these are basically bubbles that are flowing through the blood. So I could think of them mathematically as the same as the fluorophores. So basically we applied the same idea as we did in microscopy to ultrasound. And in this case, the method was called SUSHI, sparsity-based ultrasound super resolution hemodynamic imaging, because we're interested in blood flow. And when I presented this at an ultrasound conference, somebody got up and said that it was a very fishy method. And it is fishy because look at the blood vessels here, right? It's the same data. We're just applying our method to it. And you get very good depiction of the blood vessels, which of course you can't get in the standard image. So recently we've done a clinical study using this approach on patients with breast cancer. And what I'm going to show you now are 2 images where the top, the B mode, is what you get today in ultrasound. So in both of them, you see, something that looks like a tumor, but it's hard to know what this tumor looks like. On the left are the methods used today to try to perform the detection, and you see that they're not very helpful. But now if you look on the right, after we use this learned version of recovery, you can see that these 2 tumors behave very, very differently. And clinically, the doctors were able to identify immediately that this is a malignant tumor. Sorry, this is a benign tumor, and this is a malignant tumor due to the vascularization that could be seen very, very precisely. So to us, this was very exciting that basically we're taking ideas coming from sampling theory, although again, this is not a sampling problem, and using it, we could actually get, a lot of clinical value. Okay, so that's what I wanted to say about power spectrum estimation. I want to move on now to talk a little bit about quantization, which is again a task that we have in our system. Now, today, in terms of theory, sampling theory and quantization theory are really 2 separate things, right? In sampling theory, we talk about going from continuous time to discrete in time, but still continuous amplitude, whereas quantization or source coding theory or Shannon theory looks at quantizing the amplitudes, but assuming that things were already quantized in time. It's discrete to discrete. what we would like to do is unify the two, right? We want to get a rate distortion theory of analog signals. At the end, I have an analog input. I want to recover my analog input or some task related to that input, and I have to constrain both the sampling rate and the quantization rate. So I'm going to skip the information theoretic components. Those interested, you could see a review that we wrote on this topic, but I just want to give the end result. So we've developed, a new kind of rate distortion theory that allows us to characterize rate distortion of analog signals. And using that theory, we can show something very interesting. So we can ask ourselves, for a given distortion, if I'm going to use, 5 bits, what is the minimal sampling rate I need in order to achieve the minimal distortion? Now, the reason that it should be below Nyquist, I'm not assuming any structure here, is because when you think about it, the fact that I'm quantizing is going to mean that there's distortion in the signal, even if I sampled at a perfect rate. So in some sense, we're sampling at a rate that ensures that I could perfectly recover the signal, but I'm never going to perfectly recover the signal because of quantization. So I'm oversampling. Right? The question is, could I go below the Nyquist rate and not introduce further distortion beyond what I would have gotten anyway due to quantization? And the answer is yes, and we could see that in these plots. So here we're plotting the minimal sampling rate needed for different input signals. And again, we're not exploiting any structure as a function of the bit rate. And of course, as the bit rate is lower, we can actually sample at much lower rates without losing anything, meaning even if I would sample here at the Nyquist rate, I wouldn't get a lower distortion. So first of all, to me, that was very interesting to show that even without structure, just because we have quantization, we could go well below the Nyquist rate. So that was kind of an interesting observation. But the question is how to do it in practice. So as you already see from my talk, we're very interested in theory, but we're also interested in building systems. And typically in general quantization, things that achieve the rate distortion curve are usually very complicated vector quantizers. So that's not going to be useful for us in the applications we're considering. So our next step was to say, could we get very efficient quantization with what we call hardware limited quantization, meaning I don't want to use vector quantizers. I want to use very simple scalar quantizers because that's what people use in practice. Now, of course, a priori, the answer will be no, right? I can't achieve rate distortion limits by using simple scalar quantizers. But what we're going to do is a little bit more elaborate. So we're going to do 2 things. First of all, the hardware is simple scalar quantizers, but we're going to allow ourselves to do analog combining, just like we did in compressed sensing and sampling. So now we're not doing this for compressing the sampling, we're doing this to make the quantization more efficient. So we're going to mix the data before we quantize. And then of course, we're going to do post-processing. So we have this new paradigm where our quantizers are simple scalar quantizers, but we do analog combining before them. And we're going to optimize the analog combiner, which is a very simple piece of hardware, and the post-processing for our specific tasks. So, it might be channel estimation, source localization, bit recovery. Okay, so it's task-based, it's per task, and it's hardware limited. We're using very simple hardware. And what we can show, which I think is quite surprising, is that we could very often achieve the optimal rate distortion curve by using this simple paradigm. And we've applied it to a variety of different applications. So maybe I'll skip through this in the interest of time, but just to mention that there's been a lot of work on low bit ADCs for massive MIMO systems, because there, of course, a lot of the power of the system is going into the ADC. And there's been many, many works which are really, really nice that showed, okay, we're going to quantize at low bits, and here's the error that we're going to get. But actually what we're able to show is that by using our paradigm, I could quantize with low bits and actually not even get an error. So what we're doing different than all of these other works are 2 things. One is that we have the analog combining first, and we're optimizing it for our task. And the other is that, well, it kind of goes together, but we're doing the optimization based on the exact MSC values and not on approximate. So this has to do with the general framework of doing the analog pre-coding, first the analog mixing, and then simple scalar ADCs. And by doing that, again, we can achieve the rate distortion performance, and we're performing much better than the different quantizers that were proposed previously in the literature. Now, of course, in doing that, we're assuming that we know something about the channel or about the statistics of the input. But the next step was to extend that to the case that we don't know anything. And we do this by using this model-based learning. So we keep the general paradigm. We have analog pre-coding, simple scalar quantizers, and post-processing. So we use this model-based framework, but now these different components are learned from training data. And that allows us to achieve the rate distortion curves without knowing anything a priori about the statistics of the signal. So here we're going to see a short demo of these ideas. This is a board we developed in the lab to do this analog pre-coding for a massive MIMO example. And as you see, it's quite simple. We could reduce both the number of channels and in each channel reduce the number of bits and still get optimal performance. So again, we're not going to see the movie to the end, but you could see it on my webpage. That's the hardware. We simulate the system and we can show that we could get optimal performance even though we're using fewer bits and fewer channels. So in the demo you've just seen, we've actually used additional hardware for this analog combining. And one of the things we've been looking at more recently is whether instead of using additional hardware, we could use dynamic metasurface antennas, DMAs. So as many of you know, there's been a lot of work in recent years on using these type of metasurface antennas in the communication literature. But until now, they've basically been mainly considered as passive elements. So they've been looked at a lot as reflecting elements to improve the channel conditions. But what we want to look at in our work is using them as active elements. So I don't want to use them just for reflection, but I actually want to use them as an analog combiner. And the advantage is that I could do this very efficiently. So I could get different responses from these DMAs by simply changing the current. So we've shown that we can use these DMAs, and this is work that we did together with a group of David Smith, who's an expert in these metamaterials, and he's been building these in the lab based on our collaboration. So by changing the current, we can actually get different filter responses. And in fact, it's actually more powerful than the RF hardware because we could get frequency selective analog processing. So it's very simple, it's very power efficient, and we could do this analog combining in a very efficient way so that we can build systems that are efficient, are cheap, and rely on very low bits and still give us the optimal performance. Okay, so we've seen that we could do radar efficiently, we could do communication efficiently, and this of course brings us to the next topic of whether we could combine them. So this is of course another topic that's been looked at very extensively in the literature, and many different ideas have been proposed to do this DFRC, dual function radar communication systems. So I'm not going to go into great detail here. I'll just mention we have a recent review on this topic, so those of you interested could look in more detail. But from a bird's eye view, there's basically been several different methods that have been proposed. So the first method is basically to have two separate waveforms that do not interfere with each other. The second is using a COM waveform for both radar and communication, for example, by developing OFDM radar. The third is to have a dedicated waveform that we design that's good both for radar and for communication. And finally, the last approach that we're going to focus on here is to embed communication bits within the radar waveform. So this is a topic that we've been working on a lot together with Professor Tianyu Hang from Tsinghua, and we've been doing a lot of work here in collaboration with their fantastic group that have a lot of expertise in radar. So the idea here is to convey the digital messages within the radar signal. So basically we're sending the bits in different aspects of the radar signal. So we've developed two demos in the lab, again, together with the group of Professor Huang at Tsinghua. So the first approach we looked at was what we called major COM, multi-carrier agile joint radar communication, in which we embedded the information in the radar waveforms by looking at the frequencies that we use and by looking at the antenna allocation. And by doing this, we could convey relatively a low data rate of communication, but without harming the radar at all. So basically the radar performance is perfect, but what we could get through is a limited capacity in terms of the communication. So this is good for applications where that's relevant. More recently in the last ICAST last week, we developed together a new demo, SPACOR, in which we also did spatial modulation, and this allows us to increase the communication rate so we could get also better communication rate and better radar rate. Of course, the demo itself is a little bit more complicated, but it still allows us to do this DFRC system in a very, very convenient way. And here you see a demo where we're doing both the radar and communication simultaneously. And those interested, I encourage you to look at our recent demo from ICAST, where you can see, many more details on this paradigm. So let me just end before I go into the 5 minutes on the model-based learning by saying that this idea of efficient quantization could be used also for other applications that, again, have nothing to do with sampling. So for example, we've been looking a lot at how to use this for federated learning, where the idea in federated learning is that we want to do learning on the edge. So basically, we want different distributed let's say phones or computing devices to be part of the learning process without sharing their information. So instead of sending all of the data to a central point, we do the learning on the edge itself and only share, for example, the gradients or part of the network itself. But even when we share gradients, when we have a lot of nodes, the computational cost, the communication cost of sending all of these bits, which has to be done continuously, could be quite high. And here we've been using these task-based quantization ideas and the pre-coding ideas to do this in a very efficient manner. Okay, so with that, I want to switch gears. How much time do I have left?
Oh, it will be fine, yeah.
Okay, good. Yeah. So I'll take 5 to 7 minutes to say we've already seen examples of this model-based learning as we've been going through the talk, but I want to kind of summarize more precisely what we do here when we say model-based learning based on very similar ideas to what I suggested until now. So we all know that deep learning has been overtaking the world. We get fantastic performance, particularly in problems which are hard to tackle with models. Now, on the other hand, there's also a lot of challenges associated with these deep networks for applications that we've been talking about, such as communication and radar. We typically need very large training sets. The methods are not very interpretable. We don't know how robust they are. The generalization could be limited. And it's often not really clear, you put everything in there, you kind of stir, it doesn't work, you stir again, it does work. So, the feeling is that it's not so robust and it's not always easy to analyze the results that we obtain. Now, on the other hand, when we look at signal processing, which is model-based kind of by definition, we have a very different paradigm. So signal processing traditionally is based on modeling. We could easily incorporate domain knowledge and structure. We know that we could get inference from a relatively small amount of data. And typically we have very nice techniques to assess the quality of the output. So, we could say something about our result. But the big challenges are that, first of all, it requires model knowledge, which is what deep learning is trying to overcome. We don't always have that knowledge. And even when we do have that knowledge, it could be quite complicated. It's not always easy to work with, which also means that often the inference could be slow. So what we've been working on very intensively in the past few years is how we could combine these two, how we could combine black box deep learning with model-based signal processing. So to do that, let's take a really bird's eye view on model-based processing versus deep learning. So in model-based processing, typically we have our input or our measurement, we'll call it Y. We have some desired output, our task, which we're going to call X. And then we have some a priori known relationship between Y and X. So we're going to assume that Y is some known function of X, or approximately some known function of X. So Y is approximately G of X. And then we're going to come up with some metrics of some, norm or regularized norm that's going to try to, let's say, minimize the difference between Y and G of X. So often we're not going to have a closed form solution to this problem. We'll come up with, our favorite iterative algorithm, maybe some gradient descent, which will look something like this. So we'll have some pre-processing, then some iterations, where these iterations typically have some generic computation and then some computation that depends on our known model. And then we'll have some post-processing that will lead to our output. So every time a measurement comes in, it's going to go through this iterative process and we're going to get our output. Now, if you look at deep learning, the paradigm is very, very different. So first of all, we have a fixed network. So, in advance, we have the network. We just don't know the weights, but we know the architecture. It does not depend on our problem. We then have many inputs and many outputs that are paired. We use them to train these weights. And then when a new input comes in, we put it through this train network and, hope that magically we'll get a good output. So these are very, very different paradigms. And the question is, how do we merge them? So we merge them in our work in two main ways. Of course, you could think of many other ways to do that. One is through algorithm unfolding or unrolled-ing, which is based on this optimization framework. And the other is what we call hybrid methods, which we just take the model part and plug a network in. So I'll show these two approaches very briefly. So deep unfolding dates back to a beautiful paper of Gregor and LaCoon from over a decade ago that kind of got lost, I think. And the idea here is really nice and really simple and very generic. So we could go back to our iterative algorithm we showed before. We explicitly write down several iterations, let's say T iterations, where T is typically small. So in most of our applications, it's less than 10. So let's say we write down 10 iterations. This is still an iterative algorithm. It's not yet learned. But then in the last step, what we do is in each one of these iterations, we free some of the parameters. So some of the parameters that we may not know, we learn from data. We then use training data to learn these parameters. So we end up with an architecture that depends on our optimization problem, but it's learned because we learned the parameters from the data. Okay, so that's kind of the idea in a nutshell. And those of you interested, we have a recent review where we go into much more detail. So we've used this in many, many applications, and this is work that we did together with a group of Vishal Monga. So for example, we've used this for blind deep learning and got very, very nice results, which surpass state of the art, even though we used a small training set, and the method is very simple. Again, it has less than 10 layers. We've used this for super resolution and ultrasound, using a basic optimization based on sparse recovery and then unfolding it. We've used this for separation. So here I'm showing ultrasound, but you could do the same thing. And we've also used it for radar, where in this case, we're trying to separate between the tissue background, which is kind of a constant clutter, and the blood. So we model the blood as being sparse and the tissue background as being low rank, which leads to, a robust PCA type problem. But here we unfold the robust PCA to improve performance. So those of you interested, we have a recent review that we wrote on deep learning and ultrasound specifically, where we go into this in more detail. And here I just have to say, this paper is from 2 years ago. So it was before Corona, before COVID. And we called this method Corona. It stands for convolutional robust principal component analysis, but the method obviously went viral. So just to show, how this unfolding works. So in this case, we model our data as low rank plus sparse. We have a penalty for low rank, a penalty for sparsity. We use, our favorite proximal gradient method to solve this problem. So this is all standard. It's not yet learned. We could write down the network. This is still just the iterative algorithm. But then in the next step, we actually free these parameters and learn them from data. So that's kind of how we get a learned network out of this well-known robust PCA method. Okay, so that was one approach. The other approach that we take, as I said, is a hybrid method. And in this case, we don't start with our optimization algorithm, but we actually start with the method itself. And this is relevant to many applications in communication where we're not really explicitly solving an optimization problem, but rather we're using a well-known heuristics, like the Viterbi algorithm. I'll show an example. So in that case, we actually start with the algorithm. We break up the algorithm into blocks, and only the block that depends on the model we replace by a very small network. So it's not even a deep network, it's a shallow network. So instead of learning end to end, we learn only the block that we need. Very intuitive idea, but very powerful. And again, those of you interested, we have a recent review on applications of this to communication systems. So just to know an example, the Viterbi net that we did together with a group of Andrea Goldsmith. So the idea here is very simple, right? We want to do symbol detection. We don't know the channel statistics. There's been many recent works in the literature that use, black box deep learning for this. They require huge amounts of training data, and they don't adapt well to when the channel conditions vary. What we did instead is very simple. If you go ahead and just look at the Viterbi algorithm, you'll see that most of the algorithm actually doesn't depend on the channel. So this whole trellis diagram doesn't depend on the channel. The only thing for which channel knowledge is needed is the likelihood. So instead of replacing this whole thing by a deep network, we kept the trellis and we only replaced the likelihood by a deep network, which is actually quite shallow because learning the likelihood is quite simple. So that's the whole idea. And the nice thing is that it works much better than previous deep learning methods, and it's very robust. So even as we change the challenge conditions, it could adapt very nicely to new channel conditions. So we've used these ideas in many other applications in communications. We've used this for factor graph methods, and it's the same idea. Instead of learning end to end, we just learn the factor graph, but then do regular message passing over the factor graph. We've used this for successive interference cancellation. So again, instead of end-to-end learning, we use a softmax to learn the probabilities of, who is the next user that we should cancel, and then we cancel it in a very systematic fashion. So it allows us to do, this greedy successive interference cancellation, even when we don't know the channel statistics. And finally, we've been using this a lot recently for COVID-19. So we formed a task force in Israel of various different hospitals that looked at different problems of AI in medical imaging. So I'm not talking about this today, but a large part of our lab focuses on AI for clinical applications. And we have many doctors that we work with. So throughout COVID-19, we've been working on trying to get good detection of COVID from both X-rays and ultrasound. And here again, we use these model-based ideas to get very high detection rates. And this was recently published in radiology in a clinical journal. So I think hopefully I'm ending on time. So to wrap up, we've seen that we could get very efficient, interpretable, high-resolution sensing, both in learned fashions and in model-based fashions. And the idea is to exploit everything we can, both the structure and the actual task. We've seen that there's different parts to this. So there's new mathematical limits, new mathematical theories in terms of sampling rates, coding rates, and super resolution. We've put in a lot of effort in engineering research, so actually developing new samplers, developing new technology. And finally, at least to me, one of the exciting things looking ahead is seeing if we can use these new limits and these new devices in order to kind of get new clinical applications and new scientific applications, given that we could see things that we couldn't see before. So let me just end by saying that, of course, I've skipped through many of the technical details. You could find it in our books on sampling theory and radar theory. None of this would have been possible without the fantastic group of students and engineers that I've had the privilege and honor to work with over the years. And of course, my wonderful collaborators who have been an essential part of all of this work. And thank you very much for your attention.
Thank you very much, Professor Yonnia Eldar, for the fantastic talk. Okay, so I got several questions. And the first question is from Professor Andrew Zhang. So Andrew, would you please unmute yourself and ask the question by yourself? Hi, Andrew, are you there?
Okay, thank you very much.
I think you're muted. Sorry, I think you're muted.
Yeah, the system seems automatically muted me again. So you can hear me now?
Yes,
yeah,
now
I can hear you.
All right, okay. Yeah, first I would like to thank you, Professor Eldar, for your great talk. It's very impressive. You talk there are a lot of knowledge, and I think all of us learned a lot tonight. I have actually two questions. One question is about the sparsity. How we both, well, I think a lot of us have known that sparsity has been exploited in both communication and radar systems separately. We also see quite a limited work in the ISAC area, where the sparsity also exploited, for example, for antenna redesign. So do you see any opportunities in terms of the sparsity in, for example, waveform and the receiver design that we may use for ISAC systems? So in addition to the sparsity in array design, can we exploit the sparsity in signal or waveform design and also receiver design?
Yeah, excellent. Thank you. So yes, I think that's, hopefully I showed some examples today. I think that's actually very important. The sparsity, and I'll say also about things that are not sparsity, but definitely the structure or sparsity could be exploited and should be exploited in the receiver in several ways. So one is reducing the sampling rate. The other is reducing the quantization rate. And of course, the third is reducing the number of antenna elements. So that's all pure receiver based. And definitely both the radar signal and the communication signal have structure that could be exploited to do it. Sparsity is one form of structure. What hopefully I've been able to convey today is that it's not the only thing we could exploit. So we could exploit the task. If there's no structure, we could exploit more elaborate forms of structure. And we could exploit structure in model-based learning as well. So in some sense, I think there's many papers that kind of look at learning as a replacement to everything. But my view is a little bit different. I think at least in applications that we're talking about here, right, like radar and comm, where there's a lot we know about the system, there's a lot of structure, there's a lot of engineering principles that we know are there because we designed the systems. I think if we use learning in a more moderate fashion, in this model-based fashion, then we could exploit structure, sparsity in many points in the receiver design, again, particularly in sampling rate and quantization rate.
Okay, thanks a lot. And my second question is, in general, in compressive sensing, when we apply, for example, some compressive sensing algorithms to recover the sparsity to estimate the signals, generally we can only estimate quantized signals, or in other words, many compressive sensing techniques, they can only be applied to on-grid models instead of continuous signals. So I'm not sure, you described a lot of examples in your research which exploits the sparsity. So do you usually deal with quantized signals? I mean, on-grid models? Because in particular—
Yeah, thank you. That's a really good—
Yeah, particularly for radar, we needed to estimate continuous values. So how we can minimize the quantization error in this case?
Yeah, that's a really good question. So thank you. Yeah, and I know I went through things very quickly. So these questions help kind of crystallize some of the points. So thanks for that. Yeah, so that's a really good point. So everything we're doing is analog, okay? Meaning, I mean, if I could quantize, then I'll use that. But in cases where I can't quantize, the results that I've shown are all analog. So we use compressed sensing, and I think I mentioned this, but maybe I didn't stress it enough. We use compressed sensing to locate the correct subspace, not to recover within the subspace. Meaning, if I'm that was kind of a mathematical statement, but if I'm translating that, in all of the examples I've shown, we could prove that I could recover the underlying analog signal, meaning in the terminology of your question, I could recover on a continuous domain. Now, of course, there's issues of noise and robustness, et cetera, and things that are done on a continuous domain are of course, going to be more noise prone. So if I could quantize, I will, but if I can't quantize, if I need to recover the analog, then our theory and algorithms allow to recover the analog version.
Okay.
So we don't discretize, we don't take the signal and kind of start by discretizing it and then solve a compressed sensing problem. We treat the signal end to end as an analog signal.
Okay. Yeah, I think what you mainly doing is probably based on the earlier work of finite rate of innovation, right? So mainly you reduce the sampling rate and make it proportional to the what's called rates of innovation.
So that's kind of the early versions. That's the early versions.
Yeah, that's a very early version of that. Yeah.
Yeah.
But you are not relying on the dictionary-based compressive sensing for recovery.
No. No, we're not. But we're also not relying on, I mean, FRI was kind of, the beginning of the slides. The things we're doing later are expanding on that in multiple directions.
Oh, okay. Thanks a lot. Yeah, that's
sure.
all my
Thank
questions.
You for the questions. Thank you.
Thanks.
Okay, so another question is from Dirk Schrock. Dirk, can you unmute yourself? Ask a question. Yeah.
Yes. Hi.
Hi.
So in the deep unfolding, which is compared to which is a repetition of iterations of an iterative algorithm, it seems that in the comparison between the two, some parameters, hyperparameters in the iterative algorithm are not adapted when you compare. Because it seems that in the deep unfolding, the difference is that those parameters are jointly, they might have different instances in the different, how do you call it again? Levels, iterations.
Different layers.
Layers, yes. And then they get jointly optimized.
Mm-hmm.
But, I don't know. It seems that the iterative algorithm that it gets compared to have fixed parameters, whereas they could have been optimized also.
Yeah. Okay, really good point. So thanks for that. I hope I understood correctly. I'll try to crystallize, and then you'll tell me if I understood what you meant. So I think the comparison is, there's two comparisons we'd like to make, right? One is saying for the same training data, how do we do compared to just a regular deep network, right? So that's like a deep learning comparison. And there you could show in many applications that you do better, and you're also more interpretable and more robust. So, that's a comparison that's, I think, a fair comparison, because we're using the same data, same training size set, same everything, just two different architectures of the network. So that's kind of, a heads-on type comparison. With respect to the original iterative algorithm that you started with, it's not really a direct comparison in the sense of, like you're saying, I mean, if the model I have is, 100% correct, there's no uncertainties in the model, and I'm not concerned with computational time, then a heads-on model-based method will solve our problem, right? That's what signal processing has done for a very long time. The issues come in when maybe the model is not exact, maybe there's parts about the model that you don't know, maybe it's changing in time, or that you really care about computational costs and you want to do things more efficiently, which, by the way, for me is less the concern. I mean, I think the computational part is maybe less dramatic, but I think in the applications we've seen, it's that the models are not 100% exact. Now, you're right that it's not the same comparison in the sense that the iterative algorithm is not exploiting the training set. Now, what you could do, and this is a comparison that we've done, is you can say, okay, if I have a training set, what I could do in an iterative algorithm is I can use the training set to learn, let's say the PSF. Let's just take a concrete example. So suppose I'm looking at microscopy. I can say, okay, let's say I'm doing a sparse recovery based, microscopy method. And I'm saying, well, I'm not so sure I know the PSF. So I could take, if I have training data, I can say, let me use the training data to learn the best possible PSF and then plug it into my iterative method. So that's kind of, I think, what you would probably do before deep learning, right? That if you have data, you'll use that to estimate your PSF and then plug it into the sparse recovery. So, that's something we could compare with. And we have compared with that. So for example, in microscopy, if I learn the PSF and then plug it into my iterative algorithm, I'm not going to do as good as if I unfold the iterative algorithm on the same learned data set. Does that make sense? Does that capture what you asked?
Probably.
Okay,
sorry. Think about it a little more.
Okay, and I'm happy to chat more about it offline as well.
Sure. I have another question, if I may. In the deep massive MIMO application, so the analog combiner before the scalar quantizer then gets replaced by a multi-layer neural network. The whole thing is an analog domain, right?
Yeah. Okay. Really good point. Yes. Thank you. So the analog, the neural network learns the coefficients of the analog combiner, but I'm learning that offline, right? Like what I'm actually building in hardware at the end are these coefficients. So I have to learn those coefficients, but I'm not building the hardware of a neural network.
Okay,
I'm
so
learning
it's not
the coefficients.
Yeah, it's not a neural network that's filtering. It's the analog combiner, and the neural network learns the coefficients of the analog. Okay.
Exactly.
That's good.
Exactly.
Yeah.
Exactly.
One third question, if I may, in the spectrum or covariance structure recovery, normally what I teach is that to estimate correlations or spectrum, you need an infinite amount of data to get consistency. So when you have this recovery with a finite number of samples, what is your recovery criterion?
Really good point. Yes, that was really good point. So first of all, the example I gave, kind of n and square, that was just for intuition. That wasn't, that was just to build intuition. The math, of course, looks at continuous. So it's very similar to asking about Nyquist theorem, right? Because Nyquist theorem also requires infinite samples. It assumes that you have samples from -infinity to infinity, which of course in practice you don't. So you develop the Nyquist theorem, and then in practice, you basically have a windowed version and you just plug it into the same equation, even though you don't have infinity. And then, you could develop bounds on the gap, right, on the error. So it's the same thing, right? I mean, the rate doesn't say how many samples I need. I always need infinite samples. The question just is the rate of the samples.
Okay.
So
Okay.
it's the same thing here. In principle, I need infinite samples. It's just at what rate do I need to take those samples? And the rate is much lower than the Nyquist rate. Of course, in practice, like when we build systems, whatever, I don't have infinite samples, but that's the same as Nyquist recovery. I also don't have infinite samples.
Okay. Okay. Thanks.
So it's very similar. It parallels like what we do for the Nyquist theorem.
Okay. Thank you.
Sure.
Yeah. Okay. So I got another question from Tianyao Huang. Tianyao, can you unmute yourself?
Yeah. Yes. Hi, Yonnia. Could you hear me?
Hi. Yes, I do. And thank you for the great collaboration.
Thank you. Thank you. Thank you for giving us this talk. You just mentioned many deep unfolding methods, and I have a questions on this topic because this topic is very important. What do you think? Will there be some theoretical performance guarantees for these methods? Do you have some guide on this?
Yeah, thank you for that question. So first, let me say, and as you know, because we've discussed it, I think that's super important. So I think, you know, there's so many empirical results that show that this method works well, and getting theoretical results that substantiate that is, to me, at least for my own research, that's one of my main goals right now. So there are several papers that look at, and we go through them in our review. There's several papers that look at different guarantees, but I have to say, and you know, obviously beautiful papers with nice mathematical ideas, but at least the ones that I've seen, and those are the ones that we cover in our review, they're not focusing so much on the learning ability of these model-based frameworks. They're focusing more on the optimization properties. So, you know, they're making claims like, you know, if you do this model-based, if it's going to converge or not converge, or converge to the right solution from an optimization point of view. But I'm not really aware of results that look at this from a learning point of view, which is what we really care about, right? Like, you know, how well could I prove that it generalizes well? Because that's what I see in practice. Could I prove that I could use less training data to get the same recovery error? Because that's what we see in practice. So these are really kind of the learning questions that personally I'm interested in. I haven't seen results on that. And if anybody here knows of results, I'd be really happy for the references. It's definitely, for me, one of the main topics that we're really interested in. And I definitely use this platform and opportunity to say that if anyone is interested in it, please do send me an email, because we have been thinking about this. We have, you know, beginnings of ideas and results, but not anything coherent. Otherwise, we would have published it. So definitely, this is something that I think is super important and definitely lacking in the literature. So we are working on it. I don't have anything that I feel comfortable enough saying, you know, bulletproof done, but I'm very, very interested in this. So A, if anybody's interested, please do send me an email. B, in terms of your question, you know, do I think that things could be said? So, well, I am optimistic, otherwise we wouldn't be working on it. I think empirically we see this works well. So, you know, I'm pretty convinced someone should be able to prove something about it. Like I said, we have some beginnings of ideas, so hopefully we could substantiate them, but I think this is definitely an important goal.
Thank you. Cheers. Cheers. Thank you very much.
Sure.
Okay, thanks. So the next one, may I have Aman? Aman have a question about X samplement. So Aman, can you unmute yourself?
Yes. Okay. Thank you very much for the interesting talk. I'm actually interested in this idea of the X sampler, where we do narrow band sampling. And this brings me to my question, where we're talking about 6G and ultra high data rate. That means we need a very wide band, let's say up to 10 gigahertz. So now, how can I apply this sampling idea that splitting the wide band to narrower channel, which is already known somehow from 5G as carrier aggregation. So how is the similarity here between the carrier aggregation and the X sampler?
Yeah, so if you just take the entire bandwidth and split it up, you're not saving anything, because, you know, the overall rate is going to be the same. So each band you're sampling at a lower rate, but you're having many, many, many bands. So, you know, the product is going to give you back to Nyquist. So just taking the band and splitting it up is not reducing anything. Again, just reiterating maybe some of the things that we said, what we could exploit. And again, this already depends on the application. There's different things we could exploit. We could exploit, if the frequency itself is sparse, meaning sparse doesn't have to mean 1, 0. It could mean like noise versus signal, right? Because the noise and signal have different properties. So we could exploit different properties at different points of the spectrum. We could exploit different properties in time. We could exploit specific tasks, like maybe I don't actually need to recover the entire signal. I'm only interested in some function of the data. We could exploit quantization. So if I'm looking at low bit, then I can reduce the sampling rate because anyways, I'm going to be using a small number of bits. So, there's many different things we could exploit depending on the specific application and the specific setting. But the point is that it's not just breaking it up and doing it in chunks, because then I'm not really exploiting anything. The overall product will be the same as before.
Okay, the other related question about the resolution of the bit resolution. Now, taking your approach, so now I understand that it is benefiting from the sparsity using the exampler approach. Now, this approach kind of works with high resolution quantizer. But what if I consider the alternative, using oversampling with very low quantizer resolution, let's say 1-bit quantization, and doing the resolution in time. So the question here is, I'm curious to know in terms of the energy efficiency, which approach could be better?
Yeah. Okay. So this is we're actually working now with Professor Rabia at Boston University to actually build these things in chips where we could really go into the power efficiency, because there's many things that go into power. So it's not there's no yes no answer here. I mean, how when you go onto the chip level, there's many different ways of implementing things, and that of course very much affects the power. So I can only say things that are global right now, and then to answer your question in more detail, of course, you have to go into the details of how A is implemented versus how B is implemented. But on a very high level, right, reducing bits definitely reduces power. So there's a direct correspondence, regardless of how you're implementing it, between number of bits and power. So any way that I reduce bits, I'm going to reduce power. That's for sure. Reducing channels reduces power. So that's another thing that will for sure reduce power. Now, if I look at the analog side, analog pre-processing increases power, right? Because I'm doing something else on the input. So I have to do my input in an efficient way that I'm still benefiting. So luckily, the advantage you get from reducing bits is much larger than the disadvantage you get from doing pre-processing if you do the pre-processing correctly. So actually, this is one of the things that we've been learning now in the chip design, is that you have to be very careful about your pre-processing. So if I just multiply by an arbitrary analog matrix, I can actually spend a lot of power, more power than I'm benefiting from reducing bits. But if I do it in a smart way, where again, smart depends on the chip implementation, then I could overall benefit a lot. And this is part of the flexibility of the framework. So since at the end, this is all an optimization problem, and we know exactly it's part of this model base, right? I know exactly what's going in. It's not this big deep network that I'm just mixing and then I don't know what I'm getting. So, when we sit with Rabia and she says, look, guys, this is what costs power. This is what doesn't cost power. I could put all that into my optimization problem. And that's basically what we've been doing, so that I end up getting a chip that is low bit, low channel, but also very power efficient on the analog side.
Thank you very much. And this is what is interesting, like tackling different approaches and in the end come up to the good design from each partner. Thank you very much.
Sure.
Okay, thanks. So maybe we will have the last question is from Fan Liu. Hi, Fan. Can you ask the last question?
Hi, Yonnia. So
hi.
Very impressive talk. So I've just finished my last meeting and
okay. Well, thank you for joining.
Yeah. Thank you very much. So my question may be a little bit, a detailed question related to the DFRC system. So I've noticed that you have characterized the DFRC design into I think 4 categories, right? So actually, we typically call we call one of the, so you have a communication-based waveform. So we typically call that communication-centric DFRC, and another technique is called information embedding, right? So I think we typically call that radar-centric, something like that. So my question is that it seems to me that most of the radar-centric or information embedding techniques based DFRC systems, they are typically operated in the slow time domain, right? So the information is embedded by slow time coding. So typically, I think this might lead to low data rates, because when you do slow time coding, this data rate will be tied to the radar pulse repetition frequency. So I wonder, how did you deal with this issue in your index modulation based DFRC system? So
yeah, okay, so really good point. So yeah, I mean, there's many ways in which you could do index modulation. So I don't think it has to be constrained to slow time. I mean, you know, I could input the bits in which antenna I'm using. That has nothing to do with slow time or fast time, right? I could do it in either. I could embed it in the frequencies I'm using. Again, that doesn't necessarily have to do with slow time or fast time. So, you know, I agree there's a certain way in which people did it in the past in the literature. And I hope that, you know, the series of papers that we've been looking at in index modulation kind of changes that paradigm. So it doesn't have to be in slow time. We could do it in slow time, in fast time, in the system itself, like, you know, which antenna I'm using, for example. So there's various different ways in which you could implement this data. And we have been able to get to high data rates. So I think it's really a trade-off. I mean, I think in general, DFRC is a really, really interesting problem. And it's really a holistic problem. So this goes back to like joint system design, right? I mean, I think the really correct way to think about this problems, and we've been having a lot of internal discussions about it together with Professor Morang's group, right? On like, you know, I want to put everything on the table, right? And say like, okay, this is what I care about. I want this radar performance, this data rate. Maybe I have system constraints, I have hardware constraints, I have power constraints. And now, given all of this, what is the optimal design? And, you know, on the one hand, we have papers, you know, we meaning like, let's say me and the group of Tianyu and with you, right? Where we're looking at just like abstract mathematically, right? Like just saying, okay, let's just abstractly as a signal processing mathematical problem, let's find the best precoder that satisfies these set of conditions. So that's one way to thinking about it, is totally abstractly without putting any design principles other than the math, right? Like writing down metrics and finding the optimal precoders under the metrics. So, you know, there's work that we've done together and we've done with other people on looking at that type of design. Then there's other work that in some sense is going the other way around. So it's saying, okay, I want to look at efficient systems because I'm actually building this. So let me take, for example, index modulation, because that's something that has a lot of flexibility and is proven to be very useful. And now let's say, okay, given that I'm going to be using, let's say, index modulation, there's still many ways in which I could modulate indices, right? There's many ways to do that. So now, given that I'm lying within this framework, what are my trade-offs and what is the best way to design the system? So I definitely think that there's definite value, as always, in looking at both directions, right? Coming from the totally abstract, holistic mathematical principles and getting bounds versus looking at concrete systems. And then also merging them, which I think, you know, this is all work in progress. So I think we're not there yet. And I think it's super interesting to look at, is to say, okay, now what if I define a family? Like, let me define index modulation, for example, as a family, and now say, within that family, could I go back to all of those types of bounds we derived and now derive them in the context of that family? Right. And then see, you know, with this family, could I approach the optimum, or what are the different trade-offs within that family? So, you know, there's a lot of work in that direction, and we've been doing a lot of work in that direction. And I still think it's very much work in progress, in the sense that, and not just because a lot of people are working on it and still, you know, it's still in development, but I think that like overall statement saying, okay, in this case, do this, in this case, do that, it is still not there. And I think we're working on it, and hopefully we'll get there, but I think that's still work in progress.
Thank you very much. Very insightful answer. Thank you.
Sure.
Okay.
Okay. Thank you very much. So due to the time limitation, I think we must stop here. I know some audience also have other questions, but maybe we must stop here. And thank you very much, Professor Yonnia Eldar, for the fantastic talk.
Thank you very much. I really enjoyed it, and I really enjoyed the Q&A. So thanks to everyone who asked questions. And as you can see from my answers, you know, many of the ideas here are very much work in progress. So I'm super happy. I love collaborations, and there's several people here that I've already collaborated with. So anyone who finds anything interesting, I'm really happy to take it offline as well.
Okay, thank you very much, Professor Yonnia. So maybe hopefully we can invite you later in other ISAC events. Okay, thanks a lot.
Sure. And thank you so much for the invitation. Yeah, thank you, everyone, and keep healthy, everyone.
Yeah.
All right.
Yeah.
Take care.
Take care. Okay, so before we end, we also have an advertisement for the next seminar. So on June 28th, we will have the 4th seminar by Professor Arsena Petrobrou from Rutgers University. Okay, let's stop here. Thank you very much. Thanks everyone, and hope to see you next time.